Evening or good evening, good morning, good everything to everybody in the world. So it's a great honor to have Tomotoshi Nishino today as a speaker in our Tensor Network colloquium. So Tomotoshi has been basically the heart and blood of the DMRG community in the last 25 years, and that's probably why he's kind of always dressed in red. So he did his PhD thesis with Kanamori, who's a famous professor in statistical physics and material science. And very, very early after the papers of Steve White, he started, I think around 94, 95, he started applying actually DMRG to statistical mechanical problems. And he has kind of done an amazing kind of lots of different works. And whenever you think that you found something original, there's something new to do with DMRG and statistical mechanics, you actually have to think first to look up the papers of Tomotoshi, because there's a very, very good chance that he already did this. So whether it's finite size scaling with this kind of StatMech in 3D using kind of PEPS or tensor product states. So all many things that people rediscovered later were actually originally all found by Tomotoshi. So he's a real pioneer. So he also does somehow the whole Tensor Network community an amazing service by collecting all papers that kind of are related to DMRG every day. And so for people that don't know this yet, so I put somehow the link in the chat. There is this website, the DMRG homepage, on which somehow you can find a collection of all papers daily updated that are relevant for people interested in tensor networks. And if Tomotoshi really likes a paper, he kind of it's like Christmas, because then he puts the paper in red. Okay, so you will see that actually the papers are kind of get a red color. So it's really, I think this is an amazing service that Tomotoshi is doing to the community, because it makes it very easy to kind of find all relevant and latest works. But I talk too much. I should kind of give the stage to Tomotoshi. So he will talk about the corona transfer matrix formalisms.
No. Corona transfer matrix.
The corona, yes, the corona transfer matrix from the history to recent applications. So please, Tomotoshi.
Okay, thank you, Frank. First of all, I thank your organizers and of this colloquium, and I'm very happy to speak about the corona transfer matrix formalisms. Well, I was asked from Frank to speak about history of the some history of the tensor network formulations, and also including some new results. So I thought sometime what should be presented here, because everyone sitting here is like a professors or very connoisseurs in this field, and also people, students will see this talk later. Might see this talk later from YouTube. So I thought some time and chose the topic focusing on the corner transfer matrix. Well, this, okay, so, do you see the mouse pointer on the screen? Can you see?
I don't see it actually.
There's a mouse pointer, but it's not moving, I think.
Oh, no, you don't see the mouse pointer at all?
No, there is a mouse pointer, it's just not moving.
Just moving?
Really, I don't see any.
You don't see not, okay. Then I do not use a mouse pointer at all, but I already explained it. Okay. And this carrot is, the slice of carrot is just for fun, but it has the shape of corner transfer matrix, vertex weight, and also half transfer matrix. Well, this year, 2020 is the 100th, the centenary, okay. I don't know the English time, but 100 years have passed since the establishment of the Ising model by Lenz. Lenz first stated about the Ising model in his paper. I cannot read German at all, So veritaxum fastrate, no, Bastand, I can't read it. But anyway, in that paper, he clearly shows what about the Ising model.
So sorry, Tomotoshi.
Wait, so we were still seeing the cover slide.
We didn't see we don't see the new slide actually.
Huh?
Did you change slides?
Yeah. I
so we cannot see it.
Huh? You cannot see it.
So we still see the first slide, basically, the one with the
What
you should share the screen.
First, I disconnect it and share. Okay.
Maybe if you share the entire desktop, it's usually more robust.
Entire desktop. Okay.
Hello to everyone.
Entire desktop. Do you see?
Yes, now we see also your mouse pointer. Can you, if you go to full screen now?
Full screen. Wait a minute. Full screen. Can you see? Wait. Something happened. Can you see it?
Yeah, so it's perfect.
Yes.
And now we can also see your mouse.
Okay. Wait. Okay. Okay. 100 years have passed, so something is funny, but it's okay. 100 years have passed since the establishment of Ising model, and 5 years later, Ising actually treated the one-dimensional Ising model, and he found that there is no phase transition in one dimension. This history neatly shown, presented in reviews of modern physics. So please read it if you have any interest on the Ising model. Okay, I don't know how to move these. Okay, these moves. Oh, okay. Today I focus on the corner transfer matrix formalisms, but it might be better to put one more essence, one more point. That is the term phase and vertex. These terms, phase model and vertex model, the distinction of phase and vertex has been used for long in the field of statistical mechanics. In particular, for two-dimensional statistical models. We actually know vertex model very well. Vertex model is actually a tensor network itself. For example, if one consider the ice type model, probably Leap first established the ice type model, if my memory is correct. The ice type model consists of local vertices. This is four-leg tensor. So on every lattice site, there is four-leg tensor, and these each tensors are connected by legs, and each time the leg is connected, the configuration sum is taken for the leg indices. This is the definition of vertex model. So it is nothing but the tensor network. And the transfer matrix of the vertex model is represented like this. In the field of statistical mechanics, there is how to say, there is a manner that we do not actually draw such circles, but just draw horizontal line and vertical lines. This is the our expression of transfer matrix in the field of statistical mechanics if we speak about vertex model. And another type of model, this is phase model or interaction around a phase model. The name is given by Baxter, but anyway, nowadays probably people simply call it phase model. Phase model is defined by local Boltzmann weight surrounding a placket, each placket on the square lattice. And Ising model is actually represented as the stack of such a weight. So interaction around the phase model is just a stack of phase weight on two-dimensional lattice, and transfer matrix is how to say represented like this. The difference is that as long as the transfer matrix is concerned, no configuration sum is taken. In the case of vertex model, on the other hand, configuration sum is taken for the horizontal line, horizontal indices. But in the case of IRF model, no sum is taken. So sum is only taken when we multiply transfer matrices to the vector, or multiply transfer matrix to another transfer. Only when we multiply transfer matrix, the configuration sum for local spin variables are taken in the case of phase model. So there are distinctions. So please memorize this point. The slide. Slide. Do you see the change of the slide correctly? Okay.
Yes.
That's okay.
Yes.
Okay. And to speak about the two-dimensional Ising model, these two, we can express the model in both a phase model and in also by the vertex model. Phase representation of the Ising model is simple. Just the local Hamiltonian for each phases, where sigma, sigma dash, sigma 2 dash, these are spins surrounding each placket. And we divide the interaction parameter by 2 in order to avoid the double counting. And just taking the exponential of this local Hamiltonian, we get the interaction around the phase weight. And in the case we represent the Ising model by the vertex model, we consider one way. A way is to consider the vertex diagonal lattice, and put a local Boltzmann weight only for the shaded plackets. In this case, there is no double counting. So the Boltzmann weight, local Boltzmann weight, vertex weight is represented by this equation. So there are two ways of expressing Ising model in two dimensions. And these two expressions, vertex representation and phase representations, can be transformed with each other. This is sometimes called duality transformation or vertex IRF transformation. You can find the example in the paper by Ozarek and Baxter in JStatPhys, published in 1987. Or Fisher model, which is proposed in 1955. This is Fisher's super exchange Ising model. This is already an example of the vertex IRF transformation. What he proposed is the decorated Ising model. Now we call the lattice as the leaf lattice, but on the leaf lattice, there are Ising models. And if we integrate out black, the Ising spins shown by the black dots, then we obtain normal Ising model. And if we integrate it out, or taking the configuration sum for the white circles, white spins, then we obtain the vertex model. So Fisher's super exchange model is a bridge a bridge between vertex representation and face representation. Of course, depending on physics behind, a natural representation exists. For example, on the crystal surface, probably face representation is more natural. And for the ice model, of course, the vertex representation is more natural. And if you try to introduce unnatural representation, probably you encounter troublesome constraints and just increase the degrees of freedom. So natural representation exists for each model. But for the Ising model, for the nearest neighbor Ising model, both is okay. And considering the eigenvector of the transfer matrix, we can obtain the eigenvector that corresponds to the largest eigenvalue always by the power method. Just multiplying your transfer matrix many times to your arbitrary vector that is not orthogonal to the maximal vector, maximal eigenvector. And so here I showed the stack. So it is lower half of the whole system. And in the case of IRF face representation, and this is in the case of vertex representation. And looking at the structure of such lower half of the system, one easily finds that this is this kind of eigenvector is also interpreted as the contraction among half column transfer matrices that how to say that vertical that exist in the vertical directions. So just aligning the half column transfer matrices, you obtain the lower half. And just contracting half column transfer matrix, you obtain the lower half plane. So this construction is common to both expressions. Well, now I somehow goes into the variational scheme, and this is related to tensor matrix product state. Kramers and Manier first introduced this kind of how to say variational scheme, and their scheme is like that. Actually, Kramers and Manier introduced Jastrow type, what we now call Jastrow type variational state in their paper. But looking at their paper, one easily finds that it is actually a finitely correlated state. They proposed is the finitely correlated state, and their variational vector is just the product of local weights. And this variational state does not contain any auxiliary variable. So every spins are real actual spins. But nevertheless, they are finitely correlated. Yeah. That's why it works as how to say good variational state. And later, Baxter introduced auxiliary variable to the variational state proposed in by Kramers Manier. I'm not sure whether Baxter intentionally extend Kramers Manier approximation or not, but anyway, this can be seen as an extension of Kramers Manier approximation. And Baxter treated both face model, face type construction and vertex type construction. Vertex type construction is just MPS. Now we know it. And also, it should be noted that Baxter also proposed face type construction. In the case of face type constructions, the configuration sum or contraction is taken for auxiliary variables, but those spins, actual spin, living spins are not summed over, although they touch with each other. So here, as you see, sigma dash appears 2 times, sigma 2 dash appears 2 times, but we do not take in configuration sum. Okay, so both types are possible. And the Kramers-Vanni approximation was very precise and compared to the exact solution proposed by Onsaga, only 7% difference exists by the result. Okay, if one look at the Baxter's paper, which is published in 1978, we find out such statement. So this is Baxter's construction, IRF construction. Another interesting example is the case, so this is Ising model. The model then becomes usual nearest neighbor Ising model, and it turns out the case that the n equals 0 solution of 30. N equals solution of 30 means that when there is no auxiliary variable, is precisely the Kramers-Vanni approximation. So Baxter checked that his way of constructing interaction around the phase variational state coincides with Kramers-Vanni approximation when there is no auxiliary variable. So IRF construction was confirmed that it is the same as Kramers-Vanni approximation in the simplest case. Later, Baxter extended his idea gradually, and of course, we know that he proposed many important concepts for exactly solved models. Okay, here I put one more thing. 1968. Well, it is almost the earliest time for Baxter in his research life. So it is astonishing that Baxter already published such a, a long-living article or astonishing result in his very early stage of study. So Baxter formed vertex type MPS, matrix product state, in 1968, and he extended probably around 1976. Baxter introduced phase construction, and also in 1978. This article is almost the same as Baxter's what is written in Baxter's textbook. And looking at the paper, we encounter this very impressive graph. This is nothing but the eigenvalue problem for the transfer matrix, and variational vector is represented as the product of two corner transfer matrices. And in the right side, we find out how to extend the corner transfer matrix. And these are written in the form of phase representation. So around 1978, or in the Baxter's textbook, we find what we face is the phase representation of the corner transfer matrix formulation. Okay, I skipped this part. This is just the explanation what Baxter did in 1968. And probably I spoke many times, but he already, how to say, reached the notion of matrix product state in this paper. And also, of course, he established Conatrans matrix. One point is that his calculation were performed on IBM 360 computer. This is floating point up to 6 decimal places. So of course, this is double precision. And probably IBM 360 computer has kilobytes of memories. So it is astonishing that he got the very precise result. This is the power of the proof that the CTM has the power, such a strong power of deducing thermodynamic quantities. Okay, I might introduce you that Kramers-Fourier approximation was also applied to quantum problems. It was applied to transverse field Ising model by Lujan, and this appears in Physica A in 1978. And he said that it is worth mentioning that the variational method, Kramers-Fourier variational method, can be applied not only to the analog of quantum problem, but of course to the quantum system itself. The general formalism of section 4, Kramers-Fourier approximation, can be used step by step in order to obtain ground state properties of quantum systems. So he clearly stated that Kramers approximation can be used for such quantum problems. And for the S equal 1 Heisenberg spin chain, Nightingale and Brett, they applied such variational state. This is actually Kramers-Fourier representation without auxiliary variable. And this is phase representation is used for the S equal 1 spin chain. And it is interesting that is it visible in this paper? In this paper, you find out the statement by Nightingale and Brett that this method, Baxter's method, was formulated Baxter for classical models in statistical mechanics. And the final sentence is more important. Okay, anyway, the generalization to quantum mechanical system is straightforward. So what they pointed out is the construction of IRF type variational state with auxiliary variable. The application of such construction, such constructed, thus constructed variational state can be applied to quantum system. Although they did not really try to do that, but it is clear that they have the concept of applying such a variational state. MPS, okay, comes later or around the time. So the history is very parallel around 1980. After AKLT model is introduced in 1978 and fineness introduced finitely correlated state in 1992. DMRG, this is a small step trademark for human being towards unification. So it is comparable to the small step that we know very well. So everything such a parallel world start the unification from the establishment of DMRG. Also, in non-equilibrium statistical mechanics, we know that Derrida introduced the same class of matrix product state in 1993. Around the time, speak about my experience. Actually, I started the calculation of DMRG from the analysis for S equal 1 quantum spin chain. And so once I had an experience of made numerical program for quantum spin chains. But soon after, I found that it is applicable to the transfer matrix of the Ising model. I switched my direction of study to statistical mechanics. In the paper I published in 1995, I used phase representation for the transfer matrix. Because it is partially because the phase representation fits the DMRG known in those days very well. So I use it. Another reason is that the vertex weight, actually, if you try to apply DMRG for the vertex, for the transfer matrix written in the vertex representation, you need one more indices when you multiply your transfer matrix to the vector. So the IRF representation is more convenient, numerically convenient. And in this case, although the phase representation is used for the transfer matrix, vertex representation is used for the variational MPS. Of course, it is MPS. It is always in the variational vertex representation. So this is a combination of vertex representation and phase representation. And m equals 60 is kept in this example examination. And okay, I explain why I reached the Kona transfer matrix. As you do DMRG, infinite system DMRG, you obtain the renormalized transfer matrix. And the eigenvector of the renormalized transfer matrix can be obtained as power by the power method as a stack of transfer matrices shown here. And okay, we call it the stack. We called it the stack of the renormalized transfer matrix. And we find that what we find that in those days is that it is how to say we find that matrix product state in phase representation. So variational state proposed by Baxter in phase representation exists in the left-hand side and right-hand side. And in between, there is column-to-column transfer matrix. So this is actually, so infinite system DMRG actually works as, how to say, variational method for column-to-column transfer matrix. So it reminds, this structure reminds us that the Baxter already found out the same structure in his textbook. This is our route to the CTMRG. So in 1996, we formed a CTMRG according to the Baxter's proposal and according to DMRG applied to Ising model. And first we tried the phase representation, and later we also tried it to the vertex representation, and both representation equivalently works. But we found that vertex representation is better for the CTMRG because that we do not need central spin in the vertex representation. So this profit of vertex representation is reflected for the value of m. Oh, I ran. I find that I ran out of time. Okay. Then I switched to the history toward 3D calculation, 3D treatment of 3D Ising model with or without auxiliary variables. We did 4 trials. The first trial is the natural extension of Kuramas-Vanier approximation for 3D Ising model. So the Boltzmann weight are written by phase 2-dimensional IRF model, and variational transfer matrix are constructed as phase representation. So you sandwich 2-dimensional IRF model, phase model on the IRF represented transfer matrix. So what we obtain is the two-layer model, two-layer classical system. So we treated those two-layer classical system by CTMRG. And the variational state has 2 variational parameters, which is the connection between nearest neighbor spins and external field contained in the variational state. And variational parameter search is done by hand. But this is automatic human slave differentiation. Who is the slave? I don't know. Okay, the second trial. Since the IRF model, IRF variational state has much more freedom. So we thought how to search all the parameter space in the IRF variational state. So variational state is represented by a 2-dimensional IRF model, and it contains 16 parameters, but because of the symmetry and normalization, probably around 10 parameters are free. But adjusting 10 parameter by hand is very tiresome. So we create environment, what we now call environment for both sandwich structure and for both the normalization. And we obtain the generalized eigenvalue problem for the local bracket. So this is the eigenvalue problem you have to solve. And this eigenvalue problem is solved but in a self-consistent manner. So you adjust the local weight, perform the CTMRG, and making the environment, and again you solve the eigenvalue problem. So repeat it on and on. So this is the second trial. So up to this, we did not include any auxiliary variable. Third trial. This is the most important one in our in my book, probably. We introduced auxiliary variable. This is this was published in 2001. So in that paper, we introduced vertex representation for the transfer matrix using Fisher scheme. And variational state is represented as 2-dimensional tensor product state, and where chi equals to 2. So you sandwich the transfer matrix from lower and upper by the variational state. What you obtain is 3-layer system, And this 3-layer system was also treated by CTMRG. And of course, you obtain variational, environment tensor, both for the sandwich structure and both for the normalization factor. And this is also the generalized eigenvalue problem for the local tensor. And variational local tensor is improved gradually according to the generalized eigenvalue problem The way is almost the same I spoke about before. One thing that I stress is that the obtained variational state is fully optimized within the parameter space. I suppose this is an important point in the variational state. So once variational state is fully updated, then additional trial for the improvement do nothing or modify just the gauge. Anyway, any full update guide you to the right fully optimized state. And in the final trial we did, we tried both vertex and phase schemes. Actually, I tried vertex scheme and Andregendia. Take place for the phase scheme. So vertex scheme is the same as I shown here. And what Andre did is to create the environment using vertex, phase scheme. In the phase scheme, surprisingly, you have to treat four-layer system. But Andre is very good at numerics, so he neatly made a program and obtained the result. But for the CTMRG, only m equal to 12 or 16 could be kept because of the number of the layer. But anyway, environment tensor is created and this variational state was improved. And this was the result. Well, just compared to the known Monte Carlo result, we found that the vertex representation, in this case, in the case of Ising model, vertex representation was better than the phase representation. Okay. So these are four trials we made, and during file we were enjoying statistical mechanics by tensor products state TEPS. We encounter the next big wave, PEPS, by Frank. And we, afterward, Cambrian explosion happens. Probably I have no time, so I just introduce two representative tasks related to corner transfer matrix after the explosion of PEPS. One is the article Orus and Vidal by Orus and Vidal, published in 2009. And this article is actually one of the most cited articles at the reference of CTMRG. And because their paper is well cited, actually our paper is also cited because people cite our paper parallelly. Well, what they did is introducing imaginary time evolution scheme, and they used Tomotoshi decomposition. And please look at this URL about the Tomotoshi decomposition. And this is the spontaneous magnetization obtained by their scheme for the 2D TFI model. Actually, I'm a bit confused by the smooth curve. If the variational state is fully optimized, then such a sharp drop should be observed. But for some reason, such smooth drop off is shown in that paper. So I might ask them again whether the state is fully optimized or not. Probably now, if people recalculate it, then people will get better curve, I suppose. And another important article is given by Philip Colbert, as we know. What he did is that he introduced vertex type variational state, which is uniform, and ground state energy is calculated by two-layer CTMRG. And the environment tensor are created recursively as it was done in 1D quantum DMRG. So this part is their original part. This is the important part. Uh, and because of these tips, he got very precise ground state energy and also the staggered magnetization. And the gradient update scheme is employed in their scheme. And also, it is important that variational state is fully optimized once it is converged in their formulation. And one another point is that no need, they do not need any Torta-Suzuki decomposition. Okay, I almost ran out of the time for the historical part. So I might shortly review a recent result. What we are now doing is the statistical study on the polygon model. So polygon model is an extension of Ising model. So on each lattice point, there is a vector that points to the vertex of polygons. So in the tetrahedral models, the vertex, the vector can point 4 directions, and in dodecahedral model, it can point 20 directions. And the interaction is the inner product between those vector spins nearby, nearest neighbor vector spins. So this is ferromagnetic vector model, or a vector model, and the degrees of freedom is discrete. What is known for these models is that tetrahedral model is equivalent to the Potts model. For Q equals to Potts model, Q equals to 4 Potts model. Octahedral model. Actually, octahedral model is still pathological. It probably show weak first order phase transition, but very extensive CTMRG calculation still deduces unconverged result. We do not know whether it really the latent heat is finite or not for the octahedral model, Q equals to 6. And cube model, that's Ising model. 3 set of Ising models, so it's second order. Ixohedral model, okay. Speak about the ixohedral model, whether our colleague Ueda-san did the calculation, and what he did is chi equals to 500 CTMRG, and the matrix dimension is thus 6,000, because the degrees of freedom for the ixohedral model is 12. And what he find is that it shows the 12 degrees model or octahedral, dodecahedral model shows second order phase transition. And U equals to 1.617 and kappa equals to 0.898. These are exponents. So it shows a second order phase transition. About the icosahedral model, it has, okay, these are the results, and the central charge is funny. It is larger than 1.90. So the phase transition doesn't belongs to the minimal model. So something is we have to find out theoretical reason for this funny value of the central charge. And the next target is dodecahedral model. And okay, Ueda-san also did the calculation up to m equals to 800, and what he found is again the second order phase transition. And in this case, central charge is 1.99, again larger than 1. So this is a puzzle. It seems that, okay, this red line is the value of central charge from tetrahedral model to ixohedral model. No, blue line. So as you increase the degrees of freedom, the value of central charge increases. So this is what we observed by the corner transfer matrix renormalization group for the discrete ON vector model. We have a puzzle of explaining it theoretically. So we call for the anyone's idea, theoretical idea, please solve the problem. Actually, there are further extensions. If you have computer power, if you have sufficient CPU power, then there are many extensions to 24 states, 30 states, 9 states, 90 states. Or if you change your eye to 4-dimensional polygons, polytopes, there are 24 cell, 120 cell, or 600 cell. I'm not sure how to attack these many state model. Once Yeckelman and Steve, you established how to decrease the local site degrees of freedom. So we are now considering in that direction, but this is a future challenge. Okay. Okay. It seems that I have run out of the time, so I prevent going further details, further examples. So thank you.
Thank you very much, Tomotoshi. This was very interesting and inspiring to learn about the history and then also about these newer results. Are there any questions or comments?
Yeah, I have a question. So one ingredient in DMRG was doing a singular value decomposition or a density matrix diagonalization. Was that part of any of Baxter's original work in terms of the algorithms that were used? It's one of the key things for DMRG to work was that the optimization was very effective, and and it sort of coupled sort of Langshos type things, which are a great way to optimize, and coupled it with the singular value decomposition. So it's in the bigger framework of, okay, all of this was done before. Did I do anything? What? How did? What made it take off? Is another question. So let me turn it over to you.
Well, I'm not sure whether I catch your question correctly, but first of all, Baxter introduced a diagonalization of concept of diagonalization for the matrix, corner transfer matrix, and he actually did at least for the formulation a renormalization group transformation. So when he tried to extend the corner transfer matrix, he just put additional a half-row transfer matrices to the corner transfer matrix and put another weight to extend the size and perform the renormalization group, orthogonal transformation. Actually, it is renormalization group transformation to shrink the matrix size. So this is formulated. But at the last stage, probably this is the lack of CPU power. He introduced the self-consistent equation, just combining those parts and try to reach the fixed point of the final sheet renormalized result. Baxter, in the Baxter's formulation, the concept of RG is okay, at least included. But another point is that Baxter did not try to combine, treat each piece as a piece. So in the DMRG or in tensor network state, we use each renormalized parts as pieces and to construct the whole system arbitrarily by connecting the parts by parts. So one can extend the system to the horizontal direction or vertical direction independently. But those flexibility was not included in Baxter's formulation. And the second part, takeoff. What does it mean?
Yeah. So I mean, DMRG was very successful. Lots of people jumped on it. Started doing their own work based on it, and you can ask the question, well, what was the ingredients that made that happen, as opposed to everyone doing that, 10, 20 years earlier when Baxter did some of the pieces.
Okay. I speak about the DMRG. Of course, as you know, it can be applied to a very wide class of systems, including complicated connection, those systems with complicated connection or under the presence of randomness. In order to treat these tough problems, Baxter's scheme established for uniform system cannot be applied. So this flexibility is probably the point of the DMRG, and another point is probably people's interest. People's interest means that Haldane ferromagnet was the hot topics in those days, and probably they were suffering from Lanczos diagonalization, and the DMRG appears. So it was quite impressive for everyone. And this is partially the reason why people did not believe in the sometimes after you published it. I'm the one. Is it the answer?
Yeah. Well, that fills in some. I mean, but it's in general a very complicated issue. When you do something, and lots of people do very nice work, and sometimes I know sometimes I'm very excited about something, but that particular thing doesn't go anywhere. It doesn't. You don't have lots of people that start doing that. And it's hard to tell when something will, I think it's a very complicated thing with all sorts of factors, what's going on, what your community is doing.
But maybe if I might kind of give my short opinion, I think of course the time was ripe for quantum spin chains, and from the history that you gave, Tomotoshi, apparently people did not realize that you could use these method of Baxter's for quantum spin chains, no? Because even the Nys and Rommelsen, they actually used the original Kramers Wannier, not the more advanced systems of Baxter. So people just didn't know that this was possible, I guess, for quantum spin chains. But then, of course, the element that changed everything is that your algorithm is so enormously kind of efficient and robust. Okay, so, and I think that's certainly the thing that convinced everybody. Of course, this works because once you implement this DMRG, it's so robust and so kind of foolproof. And I don't think that's true with these other methods. These methods of corner transformation. Somehow it's much more tricky to get them to work than DMRG, and that has certainly been an extremely important element, I guess, in the adoption of the community. But also, of course, that people started being interested in these Haldane conjectures and the gap, and there's a combination of many factors. But certainly there was like a huge technical advance that was brought into the game by DMRG.
Shall I add some comment? DMRG uses matrix product state, and MPS has a good point that canonical construction is orthogonal, or canonical construction is possible. This is the one of the reasons why DMRG is widely used. And why it is very stable. This good point, you can find out that tree tensor network also contains this good point. And as we know that tree tensor network is more flexible than the one-dimensional MPS. So it seems that someone other than me, or including me, will extend DMRG to the direction of tree tensor network. Of course, the extension to COM network was done, but it is in that case the geometry of the tensor network is fixed from the original stage. Actually, speaking about the tree tensor network, the network structure itself should be decided according to the problem you are at hand. So the most desirable direction is that adaptive structure of tree tensor network of adaptive structure with adaptive improvement of local tensors works as DMRG. This is the right direction, might be the right direction of the extension of DMRG, but I haven't heard about that. Probably, Steve, you have already started this direction, no?
Well, go ahead, Frank.
So do I see right, Michael Eisenman? Michael, do you want to ask a question? Please do.
Yeah. So thank you. So first of all, thank you for the presentation. It's coming from an outsider to the field, and I thought that you wrapped and brought together many different contributions, many of which I actually have not been aware of. So thank you. Now, a naive question. At one point, you said that the vertex is better than face representation for a certain purpose. At one point, you mentioned. What does that mean? Do you say better because structurally it kind of renormalizes better, or is it a better approximation? Well, what is meant by this statement?
Okay, probably about the application of this variational scheme for 3D Ising model. Okay. In the case of a 3D Ising model, if we use IRF face representation, we have to treat the system of four-layer system. But if we use vertex representation, we can deal the system by constructing everything by three-layer system. Three-layer and four-layer, which is easy to handle. Of course, three-layer system is much easier than treating four-layer system. This is a reason why vertex representation is superior to the IRF representation in this specific case. Of course, for some models and according to the correlations, the contents in the system, if the system has more, if the correlation is more favor for IRF representation, face representation. In that case, I suppose face representation is better. So it depends on the system.
Now, I wonder, there are some specific remarkable predictions or calculations through the bootstrap, conformal bootstrap method. Do you get some results which can be compared with that, kind of put next to each other to see another aspect of better in terms of information which is provided on, say, critical exponents?
Conformal bootstrap, I'm not quite good at that, but I okay. So it depends on the entanglement included, the entanglement structure included in the system, and okay. I speak honestly speaking. I expect the contribution to your field to that question.
Yeah, thank you.
So there was a question of Luca.
Yes, can you hear me?
Yeah.
Hi, Tomotoshi, very nice talk. Thank you. Can you go back 1 second to the slide when you showed the M scaling of, I think it was one of maybe, yeah, this one. This.
Huh?
Sorry, no, it was on this octahedron or one of the.
Octahedron.
Yes.
This one?
Yes, this one. So you say this K is equal to 0 point something, and using the formula that Frank Polman found, this is compatible with a C that is around 2, apparently, and you get a C that is 1.9, right?
Yeah.
So it could be that it's just 2 copies of a C equal 1.
Okay. Probably you are right. We have okay. We write here that the last digit contains 2 or plus minus 2, but actually probably it's more larger, and there is a non-negligible possibility that we get C equals 2 in this case also.
Mm-hmm.
And the dodecahedral model you have apparently probably C equals 2 because
and also K equal 0.45. Yeah. This seems compatible, yes, with the.
Yeah.
No, it's interesting. But do you have any understanding of what could decouple? So it looks like, so if that's the case, it's like you have 2 decouples equal 1 theories.
2D K equals 2.
No, 2 decoupled. No, it looks like
2 decoupled system. Yeah.
Maybe.
Yeah, it is one of the conjecture since there are many several subgroup symmetries, so there might be a possibility that this is a coupled model as cubic model.
And would you know which perturbation could get one of the 2 or?
In order to reply to your question, probably we have to add some more calculation, introducing some deformation, some anisotropy, Ising or XY or more group theoretical complicated anisotropy we have to introduce and check what happens for the phase transitions, whether it is a twofold phase transition or KTO itself, etc. To check the nature of the phase transition.
Okay. Thanks.
Actually, about the same model. So if you would take indeed the higher and higher kind of limits, you should at the end up with the Heisenberg model, I guess. No. So what happens exactly? Because there's no phase transition, I guess, or what?
We do not think that the route is smooth. Because in order to okay, this is zero temperature. No. This is finite temperature. Okay, so it is right. One thing it is right that if you go to the Heisenberg limit, the TC goes down. TC goes down, but it is not straightforward to get that you will simply always encounter the same class of phase transition in each cases.
So my question is, if you would actually simulate the SO3 model, and you kind of basically only take the E-reps up to a certain kind of number. Would that correspond basically to the same models that you're simulating?
Oh, yeah. Probably because those reps are fixed by the discrete anisotropy. Probably we encounter that. But one thing I would add is that to treat those continuous model is quite difficult even for contemporary Monte Carlo simulation. No one did the right calculation for continuous ON model even now.
So if I may actually also have another historical question. So in the book of Baxter, at some point, he actually also treats three-dimensional stat-mech models using the corner transfer matrix. So he generalizes basically the corner transfer matrix to a 3D structure somewhere in his book. Did he ever kind of do actual simulations with this, or?
Baxter with himself. Are you speaking about Baxter himself?
Yes. Baxter in the book, he basically shows some pictures of what the natural generalization of the corner transfer matrix should be to three-dimensional.
Yeah, he stated that, and actually that is not straightforward because the entanglement structure could not be taken in that direction simply. Once I tried, probably you know that once I tried corner tensor renormalization group, but it was quite inefficient. So some another filtering is necessary in order to go to that direction, except for exactly solvable case. As you know, chiral Potts model or I don't know, Bazhanov, they introduced not the tetrahedron equation.
Exactly.
Yeah, that's the extension toward the 3D, and they some exact result are known for 3D model using the corner transfer matrix formulation.
May I ask another naive question?
Of course.
Yeah. So one thing which I learned, I learned many things in this lecture, so thank you. One of them was that the Kramer-Vanier introduced an approximate method. I wasn't aware of that. Now, when Baxter computes using the corner transfer matrix, the discontinuity in the Q-state Potts model for Q greater than 4, was the calculation done within some approximate scheme, or was it for the original? I mean, was it for the original model making some ansatz in the computation? But it sounds that you seem to be talking about some models which are similar to, but not exactly those of statistical mechanics. Or are these just different approximation scheme for the same good old model of StatMech?
I lose some point. So Baxter treated, for example, in Baxter's textbook, exact value of the latent heat is given, and this is theoretical, and this is based on corner transfer matrix formalism. So everything is exactly obtained without numerical calculation.
Yeah.
Do I lose some point?
I was referring to his computation of the discontinuity in the order parameters, discontinuity in the spontaneous magnetization for Q greater than 4.
Greater than 4. Yeah.
It's given, there is a formula, which is an exact formula given for that, derived using the corner analysis of the corner transfer matrix. Now, so, but from the way you refer to these things, it sounded like this is another approximation scheme rather than a method to compute for the original model.
Okay, I understand the point. Actually, if the model satisfies a certain property, In that case, one can treat infinite corner transfer matrix of infinite dimension, infinite size, and diagonalize it exactly. So since the one can treat infinite system, everything is exact. When we treat it numerically, we have to cut the dimension, and the approximation comes in. So in his text, in Baxter's textbook, everything is exact.
I see. Thank you. Thank you.
Okay, so I think this is a good time to close the discussion, and let's thank Tomotoshi again for this very nice talk and for actually waking up so early in Japan so that we can enjoy your talk. So thank you so much, Tomotoshi.
Thank
and
you.
let's
I'm
hope
very glad
we
to
see
see
each
you
other
all.
soon again.
Thank you. Thank you.
Thank you.
Thank you very much, Ishida-san. That was nice, very nice talk.
Yes.
We will cut down the Zoom.
Bye, Tomotoshi.
Bye, Tomotoshi.
Bye. Bye.
Thank you.
Thanks for the talk.
Bye, Tomotoshi. Thank you so much.